Hello, everyone. I hope that everybody who wanted to be here is here. Welcome. So today, I and my co-presenters would like to present a new framework called Instruct2Act, which is a new approach in robotics that combines large language models and foundational visual models. So I will walk you through the overall high-level logic of the framework and discuss some previous work that's been done in this field, and then my co-presenters will talk more about the methodology behind it in more detail, and also talk about the specific experiments that the authors ran and discuss the strengths and the limitations, as well as the future scope of this approach. So Instruct2Act uses large language models in combination with visual foundational models to help understand high-level human instructions done entirely in natural language and generate precise Python scripts. And they're also able to completely generate a complete loop for perception, planning, and execution and control. So the high-level logic of this approach, it relies on existing predefined APIs. So it relies on two existing predefined APIs that help access the two foundation models. So one of these models is Segment Anything model, which can accurately locate candidate objects, and the other one is Clip, which classifies them. And Instruct2Act combines the capabilities of these foundational models in order to understand complex high-level human instructions and translate them into policy codes for robots to follow. However, so large language-driven robotics have been around for some time. They offer a very useful, user-friendly interface, and other studies and approaches such as VisProg or Viper GPT have been used with pre-trained image encoders. However, this is challenging, and such systems must be able to perceive, visually reason, and select and sequence actions for long-term goal achievement. And this is additionally restricted by APIs that sometimes struggle when interpreting longer and more complex commands. However, unlike the previous approaches, Instruct2Act generates decision-making actions with the help of LLMs that help reduce the error rate by accurately locating and classifying objects in the environment. And the solution is to not fine-tune the existing models, but rather insert processing modules between the LLM and the downstream tasks. So essentially, the robotic skills are in this way combined with LLM power, and this approach is highly flexible and allows for varying instruction types, such as just human text or speech, and as well as images that the model receives within the zero-shot paradigm, and it requires minimal code overhead without even pre-fine-tuning. So that's the overall logic of it, and Nazanin will talk more about the methodology behind it and the structure.
In this section, I'm going to talk about the structure and methodology of this framework. Can we go to next slide, please?
Yeah.
So what's the main purpose of this framework? Generally, Instruct2Act allows a robot to execute a sequence of actions based on the user instruction. And basically, an observation image is also captured by a top view camera. So it aims to change the object state in the environment to match the configuration in the instruction that is given by the user. And in other words, the robots are able to execute instructions that are provided as input in natural language. And next slide, please. So such a general purpose robotic system that is capable of executing complex tasks in dynamical environments must possess the ability to perceive the surroundings and select relevant robotic skills and sequence them accordingly so it can accomplish long-term goals. And achieving such functionalities would require the integration of various technologies such as perception, planning, and control to so that the robots will be able to operate autonomously in unstructured environments. So I've listed the core modules here: perception, action, and the functions that Tanya talked about, like segmented anything model, that I've listed them here as a core component of our system. Next slide, please. So the very first big component of our framework is the large language model that we are using. So the LLM input is going to be a design prompt. The prompt should contain important information about third-party libraries, API definitions, and in-context examples that are relevant to the task. And all these components would help a large language model to understand how to use different libraries and APIs to perform calculations and basically create new functions. And then after that, the LLM would output an executable Python function in a string format to drive the robot's action. And we should note that the final output should be executable by Python interpreter that I'm going to talk about in the next slide. So here I'm just giving an overview of the LLM generating policy. So we can see here that by starting with the task instruction that's basically given by the user, the framework will utilize LLM to generate executable code. That code then would invoke visual foundation models with APIs to recognize the environment. So specifically, these APIs are classified according to their functionality within the robot system hierarchy, and this categorized information is provided in the prompt. So I've listed an example here. For example, SAM, the segmented anything model function, is belonging to the perception module, which is the second level core module in the robotic system that we have seen in previous slides. So we will add two labels, hashtag second level core module and a perception module label before introducing this function, SAM model API, in the prompt. Next slide, please. And now that we have seen that in the previous slide, that the Instruct2Act is a language-based robotic system that would basically generate perception to action codes using an LLM, and all the task-related variables, including image crops that is used in the task instruction and image robot coordination transformations, are all stored in the cache that we have, that we call it the cache C, and they all can be accessed through an API. And then after that, the system will gain a visual understanding of its manipulation environment by using all these perception models. And after that, the framework with leverage the off-the-shelf visual foundation models, specifically SAM and CLIP models that Tanya talked about and explained about, and then it will accessed by LLM via two designated APIs that I've listed them here, SAM function and CLIP retrieval function. And then these Python functions load and call the models to conduct the visual analysis. And basically, SAM outputs the mask for all potential objects in the input image, and based on which the object crops are then extracted accordingly and are retrieved from the cache that we have. And the crops are encoded into some vectors using the CLIP retrieval function that we have. That's like, it's an encoder basically, and then that would be used for the classification task. So I've listed the modules and the more important function for each of the basic modules that we have, which is perception, action, and then the robotic APIs. Next slide, please. So after that, based on all the information that was acquired by the different components that we have seen, then after that, the system is able to generate executable action codes that is going to be executed by the help of the available low-level controllers. So now that we have the LLM, we feed the LLM with the prompt that have all the in-context examples and everything, and the LLM is going to generate the code, the policy code that we are looking for, and then after that policy code, we utilize foundation models and have the cache that can retrieve any image crops and everything. Then after that, the final stage is to use the robotic executor, which has like a low-level controllers and execute the task. So can we go to the next slide? So we have all the components gathered together here in one pictures, and this is the paradigm of the proposed Instruct2Act framework. So starting with the task instruction, the framework, like you can see from the top to the bottom. So we start with the task instruction that is given by the user. You can see the instruction that is given by the user. And then the framework utilizes large language model to generate executable code that would invoke the visual foundation models. And then after that, we recognize the environment and the object and everything. And with recognized object semantic information, then we generate plausible actions that are sent to the low-level controller. And then after that, we can execute the tasks. So you can see the number of the components that we have and how they're like interacting with each other. And the green instructions are for unimodal instructions. It can be only large language. And the second one, it can be like a combination of large language model, and also we can have like image encoder to have like a visual instruction as well. And can we go to next slide? So here is an example of all the task that was given to the robot, and it could like successfully execute. As you can see here, we have like some green instructions and blue instructions. The green ones are just pure language instruction that was given to the system, and it was like executed successfully. And the blue ones are like language visual instructions. We also can have pointing language enhanced instruction, which we can use the mouse and click and drag objects. And in that like scenario, also the robot will function very well and it works. So you can see all the examples. For example, we can put the image into another image, and all of those images are like retrieved from the cache, and the system would understand what you were talking about. Or we can just use natural language and that's it, and like just say that put the red and purple stripe flower into the trigger ball, and it will also work. So we have all these flexible instruction modality manager that would use pure language instruction, language visual instruction, and pointing language enhanced instruction. Next slide, please.
Yeah, so in this experiment section, we have selected several representative meta tasks from VimaBench. We are ranging from the simple object manipulation to the visual reasoning to evaluate the proposed method on the tabletop. So see, we are using the VimaBench. VimaBench has actually the 4 levels. Level 1 is placement. The second level 2 is used for combinatorial. Level 3 is a novel object, and L4 novel task generation. So as per, we are using the LLM model as well. So there are 2 LLM model we are using. The first one is a text Davinci 003, which is from OpenAI, and the second one is the Llama adapter. This is evaluation metric. Like you can see the results are well accurate and very flexible result. You can see for all the tasks, all 4 tasks. Then please go to the next slide. Yeah, so here are the experiment results. So we are evaluating the experiment based on the effectiveness and flexibility of the Instruct2Act. So the author conducted like very expensive experiments on the robotic manipulation task. The first experiment aimed to demonstrate this framework capability to understand and execute the wide range of natural language instructions involving the instruction with the objects and with the environment. These are the tasks, several tasks, and these are the accuracy level we can see. So this our model actually got the well accurate result, and it is going well. These experiments results present in the paper. So these are the these results are presented in the paper that Instruct2Act actually performed it. So this framework achieved the high accuracy in executing the complex tasks, and it's actually showcasing their efficiency in the real world application. So these are actual studies on the future purpose, like evaluation results on the prompt elements and the process modules. Then additional foundation models we require. Then the comparison between the 2 LLM models. Then we have achieved the flexibility and robustness on our results. Then the next one is the extension with the third-party libraries. So we are using the API and all, so we can extend the third-party libraries, and then we can improve our results. Please go to the next slide. Yeah, so this is our conclusion. So our model has some limitation as well as some future scope for this. The first one is our model is a highly flexible, provide highly flexible framework. So we don't need to train the data for the process. So whatever the data we have, we can actually perform on it. The next is so large language model generates a readable and interpretable working code, which is simple and efficient. So the output performs the state of the art model, like whatever you performed, whatever you give the instruction in a natural language, our model, our robot is performed a task, whatever you said to do that. And then so we have some future scope for this. So the future scope is which is as model is a highly computational required high computational cost. So in future we can work on this thing like we employ the several models and we can reduce actual the computation cost. Then other domain will be the only specific action. So like our robot is perform only some specific action. For example, like a pick and like place. Pick this object and place over there like that. So we can perform this action using giving some data and then creating new model and like that. So currently available and expanding the few more in actions so that our model, our robot could perform multiple tasks and many tasks creatively. So yeah, please go to the next slide. Yeah, so this is our future scope. Like as I said, this is our model is a highly computational cost. We can work on this as we reducing the cost. Then employs the several foundation models which is not suitable for real-time real-time robotic tasks. So our model actually worked on the some task which is not suitable for real-time. So we will work on the some real-time situation and we performed some real-time tasks with robots. Limited computational source. So we can use some limited computational source so we can reduce the cost as well. Limited by basic action pick and place. So our model is limited by the pick and place. So we can add some extra action and giving some extra instructions so that our robot can perform those instructions. Expand with the more interactive actions with using API. So we can provide more API, third-party API, and then our model will be the more effective and robust. Model tested in a simulation environment. So our model is actually tested in a simulation environment with specific LLMs and third-party API. But our model should be tested in a real-time environment so that we can work real-time on the real-time basis. The last but not the least, we should investigate some real-time application so that we can use this model on a real-time application. So yeah, these are actual we can work on this area for the future. Yeah, please go to the next slide. Yeah, here you have any question, you can please feel free to ask. And this is our collab, Google Colab, the code for the Instruct2Act, and this is a link of the paper. Well, yeah, this is from our side. And if you have any question, you can ask. Yeah. So please go to the question answer slide. So anyone can ask questions. Yeah. So if anyone has no question, then yeah, thanks. Thank you so much for this opportunity which is provided by this Launchpad. And yeah, we are actually grateful to them. Thank you so much.